here's a pretty typical area volume problem that you would expect as one of the 6 free response questions. So first of all, we have a shaded region. They're always going to give you a shaded region, and it's bounded by y equals 3 and y equals 3 sine of x. And notice they didn't give you the intersections here. It's also got this vertical line, x equals k. And k is going to be somewhere between 0 and pi over 2, and we'll see why in a second. And it says find the area of S when k is pi over 3. So this is pretty straightforward. You're just going to do integral of the upper function minus the lower function. The line y equals 3 is always above the 3 sine x curve. And no need to switch the variables and go relative to the y-axis or anything like that. This is really straightforward. The only thing that's a little bit of a challenge, you're going to have to figure out where this intersection is. So if we identify that point up here, right there, we're asking ourselves, when is y equal to 3 sine x equal to y equals 3, which y equals 3, of course, being this line at the top. So we just have to solve this, divide both sides by 3, and you get sine of x equals 1. And you just need to know your circle to know that the sine of x equals 1 when x is pi over 2. So this is going to be x equals pi over 2 there. So this is the point pi over 2, comma 1. Now it makes sense why they told us that k had to be less than pi over 2, because that's where that intersection occurs. So this will be pretty straightforward. We're just going to do the integral of the upper minus the lower. So integral of the upper, which is 3, minus the lower, which is 3 sine x. Put parentheses around that, dx. And now our limits. We are moving from k, which is pi over 3, out to pi over 2. So we can put our limits in at pi over 3 up to pi over 2. And then we just have to do this integral correctly. So the integral of 3, of course, is just going to be 3x. And then we've got minus 3 sine x. So sine integrates to, well, the derivative of cosine is negative sine, and that's kind of what we have here. We have a negative 3 sine. So if you think backwards like that, you figure the integral must be 3 cosine. But it's going to be positive 3 cosine of x, and we're going to evaluate that from pi over 3 up to pi over 2. And again, just to kind of rehash that, this guy here, his derivative should be this thing. And of course, derivative of cosine is negative sine, and so the derivative of 3 cosine should be negative 3 sine. So that checks out. So now we just put in the upper limit, 3 times pi over 2 plus 3 times the cosine of pi over 2 minus what we get when we put in the lower limit, 3 times pi over 3 plus 3 times the cosine of pi over 3. So 3 pi over 2 here, straightforward enough. The cosine of pi over 2, again, remembering that at the top of the circle your coordinates are 0, 1. So the cosine of pi over 2 is 0, so that's going to go to 0. Then we've got minus 3 times the times pi over 3, which is just going to be pi. And then lastly, you actually need to know your circle again here. The cosine of pi over 3. Pi over 3 is your 60-degree angle, and your cosine is going to be 1/2. We're looking at that angle there. So 3 times the cosine of pi over 3 is going to be 3 times, oops, that's going to be minus 3 times 1/2. So what do we have? 3 pi over 2 minus 3/2. So you can just box that and be finished with it. So for part B of this problem, they tell us that the area of S is a function of k, which kind of makes sense. If you go back to that last picture, depending on where k was, you're going to get a different area. As k moves closer to pi over 2, there's going to be less area. As k was closer to the y-axis, you get more area. So we could write that as a function of k this way, just kind of thinking, okay, whatever k is, since it's less than pi over 2, we'd be integrating from k up to pi over 2 of, upper minus lower. So that's basically how we would define the area of S. We'd say S equals that. So expressed as an integral. So we're looking for the derivative of an integral. Well, that's that fundamental theorem of calculus idea, kind of the second part of the fundamental theorem of calculus, where you have the derivative of the integral as the function evaluated at the variable of integration. So like we had something like big F of x is the integral of 0 to x of little f of t dt. And then we said, okay, big F prime of x is going to be little f of x. That's the second part of the fundamental theorem of calculus, where it says, okay, you can integrate some function to a variable, which is going to kind of leave that area as a variable. In other words, it's not going to spit out a number, it's going to spit out a function, which makes sense because it's equal to a function. But when you take the derivative of this guy, you're going to get back to this function, but evaluated at that variable. This t in here is kind of like a dummy placeholder variable. Now, what we have to realize is in the fundamental theorem of calculus part 2, the variable is the upper limit. And here, k, our variable, is the lower limit. So what we want to do is acknowledge that and take care of that by saying this is the opposite of the integral from pi over 2 to k of 3 minus 3 sine x dx. So we could deal with this way, or we could recognize that when you have a subtraction problem, as we do in here, and a negative sign, you can just reverse the order of the subtraction and write it this way, 3 sine x minus 3 dx. So if we want the derivative of this integral function, we want the derivative of this integral function, we can just use the integrand but drop a k in instead of an x, just like over here. The derivative of this integral function, we get this guy with that letter dropped in there. So hopefully that made sense. So I'm going to go ahead and just change this to s prime of x. I'm sorry, s prime of k, and say that that's going to be 3 sine of k minus 3. And the question asks, find out what that rate of change is when k is pi over 6. So we just need 3 sine of pi over 6 minus 3. Sine of pi over 6 is 1/2, so 3 times 1/2 minus 3 is 3/2 minus 3, which of course is 3/2 minus 6/2, which is negative 3/2. Okay, lastly for part C, we've got a solid of revolution problem. Almost always happens when you get one of these shaded region problems, so expect this. We are going to revolve around a horizontal line y equals 5. So I've taken the liberty of drawing the picture kind of from what we saw on the first page. We've got the y-axis and the x-axis here. Y equals sine of x in red, y equals 3 in blue, x equals k in lime green, and then the intersection point out here at x equals pi over 2. There, our shaded region shaded in gray with S, and of course our line that we're going to, it's going to turn out to be our axis that we're going to revolve this thing around. So, this is going to be, there's going to create a gap in here because this shaded region is going to move around this thing and kind of go like that, leaving a hole in the middle. It's going to be sort of a sideways hollow volcano. So, the thing here is we're going to go big R and little r. So we got to find out, from our axis of revolution, the larger radius is going to be this distance down to sine of x. Or, I'm sorry, that's not sine of x, it's 3 sine of x. Tuck a little 3 in there. Okay, so that I'm going to call big R. And that distance, and you can just think of, from the distance from the horizontal axis, this whole distance is 5, and then this bottom distance down here is 3 sine of x. So what's left, that yellow line, is 5 minus 3 sine of x. So big R is 5 minus 3 sine of x. And then what I've been showing is little r is always this shorter distance. That one's pretty easy to figure out. Of course, intuitively you know it's 2. I'm going to go ahead and show it for consistency as the whole distance from the x-axis as 5 minus what's not being included, which is 3. So I'll write it as 5 minus 3. Of course, we know that's 2. And then we just go into, autopilot. Pi on the outside, we have big R squared. I'll just write it as big R squared minus little r squared dx, because we're going along the x-axis. It's a horizontal axis that we're revolving around. So there's our template that we're falling into. So I can fill in our specifics now. Of course, we're going to need our limits as well. But big R is 5 minus 3 sine x squared minus little r squared, which is 5 minus 3 squared. Put a bracket around that and that, put a dx at the end. And it says write an expression, write but not evaluate an expression involving one or more integrals that gives the volume when k is pi over 4. So if we draw